welcome to the Bradley J. Show. We are live with Doug Arion, who's an astronomer, a physicist, and a teacher, a professor. And today we're going to look at what we know, what we don't know, and what we can't know, which is kind of where philosophy meets physics, which is interesting because to go to sleep at night, there's this philosophy series called Philosophy in an Hour, and it runs through all the philosophers, and it's kind of drilled in my head. I listen to it over and over again. And even not talking physics, I mean, I guess that it is related even back then, but way back to Rene Descartes, they're asking ourselves, what is there? Give me one thing we really know. Figure out one thing. And finally, he, deconstructed everything to the point where the only thing he could say that he really knew was cogito ergo sum, I think, therefore I am.
Yeah, exactly.
And that has plagued mankind for a long time, and it bleeds into physics heavily. And so Doug is going to, more than be interviewed, he's going to kind of take us to school on what we know, what we don't know, and what we can't know, and what he means by what we can't know and why we can't know it.
Yeah.
So let me introduce Professor Doug Arion. Hi, Doug.
Hey, Bradley, how's it going?
Great.
We've had conversations now for many years on your broadcast here, and we've touched on these various subjects of trying to understand what's out there and what we can know and what we can't know. And there really is some deep philosophy in some of those things that we sometimes acknowledge and sometimes don't. So as scientists, one of the things that we assume, and this is really philosophy and not physics, that the universe exists, that it's rational, that it's self-consistent, and it's the same at all times.
What do you mean by rational?
So that there are rules that guide things, that things can't change on their own. So, if gravity works here, gravity always works everywhere all the time, and that there is a rule to how gravity works, and that rule doesn't change, right? That there's a logic to it. Right?
Some consistency over both time and place.
Right, and self-consistent, so that if you observe one phenomenon and another phenomenon, those two things should happen for the same reason, right? That doesn't happen for different reasons, and so there's a logic to how everything pulls together. And we going in just assume that those things are true, and so far it looks like that works. Right? We haven't found any reason for it not to work. We look at hydrogen atoms that are, tens of billions of light years away, and we measure their energies, and it looks the same as the hydrogen that's floating in the air that you're breathing right now, which is a pretty amazing thing. That's a pretty amazing thing. But without those standards, we couldn't know anything, right? You can't know something if it could just be changed because you're looking at a different time or a different place.
Well, okay, that kind of brings us to right away to the way things work when we're dealing with things the size of baseballs and musical speakers, and the way things behave on a particle level completely differently.
Right.
So then, really, it's not irrational. It is not consistent.
No, that's not true. I mean, you can say it's still rational and consistent. It may not be exactly predictable, right? You can predict a probability, right? And the equations that generate that work, because when you then measure what comes out, it matches the probabilities you calculate. It's just, the problem is, and you and I have faced this conundrum of, what is it until you measure it, right? It's the old thing, right? You can only know the probabilities, and then when you measure it, you get one of those answers. And that's always been disconcerting to all of us who are involved in quantum mechanics. It says, we can only tell you how likely it is, but not what's really going to happen.
Okay.
Which is kind of strange.
So I didn't mean to take you off the track. So there's a world where there's consistency and things are rational. I got you off that track.
Right. No, you didn't. These things are all part of this wonderful puzzle that we call physics and understanding the universe, right? Is eventually we have to be able to put what happens on the very small scale, right? Atom scale, up to what happens on the big scale, the space scale. Those things have to eventually play together. And on your list of what do we know and what we don't know, at the top of our list of what we don't know is how to put those two things together. We don't know how to take the big things, gravity, right? Space, cosmology, everything, and have the math for that and the understanding for that work with the really small. So you can say, well, we know how much gravity there is because, you feel the weight of your tushy on your chair right now during our broadcast. We know how gravity works, right? And we know the atoms in your body are working, but we don't know how each atom in your body is feeling gravity. That's a weird thing that we don't know how to do. So there are Nobel Prizes waiting for this. If any of your listeners can come up with a good explanation for how that works, there are Nobel Prizes waiting, because that is the super, I'd say, the two super deepest questions that there are how to put gravity and quantum mechanics together, right? And once you have that, then you can start looking at, well, what happened at the beginning of the universe and what happens in black holes. Until you do one, you can't do the other.
All right. What do we know that is, relevant and helpful?
Well, what we do know is that a couple of things. Firstly, our key theories about how the universe works, which are things like quantum mechanics and general relativity, they work. And we know they work because you have an iPhone that functions and that uses quantum mechanics. And we can predict where everything is in space and how it moves. And we can make those measurements. And that says that general relativity works. So we know those things. We know that gravity attracts things. We know how electricity and magnetism work. We know how light works. We know how those things work. And those are things that are known. And the beauty of it is we can use that understanding to then make things and do things, which you do every day, right? You turn your microwave on and lo and behold, your soup heats up, because we know how radiation works with water. But there are these other things that we don't know. And that's what keeps us going, right? There are things we know, and then and as you investigate new environments, you discover there are things you don't know, in this case, how gravity and atoms work together.
There are other things we don't know, though, right? What are some of those? For example, how big space is? Is it infinite, etc.? Right?
Right. So there are things that we don't yet know because we haven't been able to measure them. So we have a sense of how stars should have first formed, right? Gravity should have pulled gas together to make stars, but we've never seen them. So we don't know right now whether that picture really works or not. There are all sorts of things that we don't know because we can't measure them yet. And this next generation of telescopes is going to be able to look far enough out that hopefully we'll see those stars. And chances are, I'd take a bet with you that we're going to find some surprises, right? We're going to say, well, it looks sort of like what we thought, but not exactly. Okay, back to the drawing board. Why does it not look like what we expect it to be? So that's on our list of things we don't know yet, is exactly how that formed. But the biggest, from an astronomy standpoint, on that list of biggest things we don't know where black holes came from. We don't know where the big black holes came from that are in galaxies. Why do galaxies have black holes at the center? Do the black hole form and galaxies form around it? Do galaxies form and somehow they make black holes? How did enough stuff get into one place? We're talking about millions of times the amount of stuff in the sun in one tiny space to make a black hole. We have no idea how that happens.
How tiny does that space have to be?
The space ends up being on the scale of sizes of solar systems, okay? But we're putting millions of suns in something that size, and then as far as we know, it continues to shrink, right? And then we get into the gravity and quantum problem again. As it keeps shrinking, it eventually gets really small, right? What happens when it gets really small?
Yeah,
I don't know.
So you don't really know whether
nobody knows, right?
What came first, the chicken or the egg, or what came first, the mass or the gravity to suck the mass in?
Exactly. That's the good question. And so on the other list of things we don't know is what is dark matter and what is dark energy? Because dark matter, which we can infer exists because we see how light is bending and how galaxies are moving and there's not enough real, regular matter, the stuff of you and me, to make that happen. So there's this stuff called dark matter. What is that, and where did it come from? We don't know.
Well, that's kind of a theory still, right? I know that there's something like that necessary to justify what we see, and the math works, etc. But no one has a clue at all if there's such a thing as dark matter. I mean, really, I shouldn't say they don't have a clue. They have a clue, but it could be some other action in play that we just don't get yet, right?
Exactly. And that's what makes being a scientist so much fun, because these things come up and you have the head slapper. You're like, whoa, look at that thing. I wonder what's going on. And it goes back 1933. Fritz Zwicky measured how fast galaxies were moving. And he's going, they're moving way too fast. There's got to be something else there holding it. And then Vera Rubin and others measured how fast galaxies were spinning and going, they're spinning too fast. There's got to be something else there to hold it together. And then you go, what is it? And we're like, I don't know. Maybe there's something wrong with how we look at how things move, right? Maybe there's nothing there, but our understanding of how things move is wrong. Maybe there is something there and we don't know what it is.
Okay. And also, I'm not a big fan of the Big Bang. It just seems kind of strange that out of nothing, something happened. For eternity prior, nothing, and then for no apparent reason, the first moment, the first little spit of time happened, and the person and all the stuff happened for no reason. I'm not. I think I get that the math works in many ways and it makes a lot of sense, but I would love to get a reason for it. Like, I'd rather believe in the infinite expansion and then collapse over and over again than poof. I mean, you have such little clue about that. It almost lends some credence to the creation thing, because just something happening out of nothing like that is pretty hard to swallow. Maybe as hard to swallow as creation. It's
right.
Tough.
And that's another interesting aspect of putting philosophy and physics together. That the philosophy of physics says there are things that aren't known, and it's okay to say they're not known yet, and you keep plugging away at it. And that goes, again, the same set of principles we started the conversation with, which says the universe is rational. There is a list of rules, and we can ultimately discover them. We may not know them yet, but that there is a set of rules, and that set of rules will somehow or other explain whatever the seed was that led to the great expansion that created, the universe that you and I see today. And different people have different ideas of doing that. And as you know, the multiverse idea, that there are many, many universes out there. We just happen to be living in this bubble. And that has some cosmological and quantum weirdness that comes along with that. There are those who have what you were just describing, the continuous expansion, contraction, or expansion and then rebirth kind of model of it. And then we don't know yet. And various people have put together various theories, but it's going to take a lot to distinguish between them.
So remember the old saying, matter can neither be created nor destroyed?
Well, matter and energy together, considering matter and energy are equivalent, you're right. But that's only true in a closed system.
That's after it's been created.
Right. So, and something you can put a box around, and you say, within this box, we can't add or subtract stuff within, not literally a box, but within the system that you're looking at. But that doesn't apply to the universe, because the universe is an open system. And that makes it weird. And this is where it gets harder to talk about stuff. But as we said, we can only observe out to 13.8 billion light years, because that's as long as light has had time to travel to us. We know there's stuff that's farther out, right? The universe continues. It's just that light hasn't had time to reach us yet. So we can't see it. So just because you can't see it doesn't mean it isn't there. So what does that mean about what the scale of the universe is? For any observer in the universe, it's a sphere 13.8 billion light years in radius.
So talking about the next...
So in a bizarre sense, the universe is both finite and infinite.
Going back to what you said about the next generations of telescopes, we'll see further and further back and hopefully see the formation of the sources of the light. I mean, you don't have any idea what that will look like?
If our understanding of galaxy formation is close to right, then we're going to see early stars that are very massive, short-lived, because they only have hydrogen and helium to play with. They don't have any advanced fuels, right? Because those hadn't been made by stars yet. And we'll see those stars and we'll say, okay, they showed up at this point and they died off at this point. That's consistent with what we expect. The other thing you hope you see is galaxies starting to come together, and hopefully that'll give us some hint about this black hole problem, right? We have this massive black hole at the center of the Milky Way, but where did black holes come from? How do you get enough stuff to fall in without getting so hot that it just pushes itself apart? We don't know how to do that yet.
All right, so if you look far enough back, do you anticipate you'll see at some point nothing? I mean, that would be the edge, right?
Right. So what you would see is if you look back in our current, and if our current theory is correct, right? That's based on our current theory. You go back, you see galaxies, and then you see early galaxies, and then you see stars forming in clumps that become galaxies. Before that, you would see gas coming together, but that gas is very cold, is not making light. So actually there's an area called the dark ages where there is no radiation. You can't observe it. And before that, you then see the first radiation, right? The cosmic background radiation, that 2.7 Kelvin, fantastic image you see of, quote, the beginning of the universe. And that's the farthest thing we can see, but that was made 300,000 years after the Big Bang. Before that, everything was so stripped apart, there was no light traveling. So that's the first light we can see. So everything before that has to be worked out in theory to then produce everything we see from that point forward. So there's going to be a period where there's nothing to see because there's no light being emitted, but you should be able to see everything up to that point, and it should make sense based on what you think happened then.
This is pretty interesting. So, light just didn't happen instantly.
No.
Conditions had to come together to produce light. And what are those conditions?
So those conditions are the universe has to be cool enough that electrons and protons could find each other and become atoms. Before that, it's so hot that everything is stripped apart and electrons can't be moving back and forth in an atom to be producing light. So it's just so hot, the stuff is just a collection of pieces. And so there's no light being made. Then you have to get to a point that things cool, atoms, neutral atoms can form, they can start making light and radiation, and those atoms have to be far enough apart. The universe has to expand enough that as they make light, that light doesn't bounce into something right away.
Okay. So this is good. Light is made by electrons moving around. Well, not moving. I guess around is a fine word.
Right.
A nucleus. And what is it that makes the light? Is it? And this is where we get to the quantum thing, because it can only move. It can only move in certain chunks called quanta.
Right,
and
exactly.
During that movement, that change in energy, and a byproduct of that change is light.
Correct. And that's how all the light that you have, the light that's illuminating your face right now, is being generated. Electrons are changing their energies. When they change their energies, if they lose energy, that energy has to go somewhere. It's a closed system, right? In this closed system, the atom, that light has to come out. That energy has to come out. It comes out as light. It bounces off your nose. It then goes into the camera. The camera senses it, turns it back into an electron, amplifies it, sends it out, and says, oh, I can see Bradley J on my screen.
So that energy comes out as
particles of light.
So energy those particles have mass, right?
Well, light particles don't have mass.
I see. Okay.
Right. They don't have mass, but they carry energy. So
okay.
Now the trick is, though, that imagine that that's happening with you. There's light coming off of you, but your room there is full of fog. That light can't make it to the camera because it bounces into the fog. So in the early universe, there's a period, remember, the universe is expanding. So it's really small, okay? Not small like softball size, obviously it's big, but way smaller than it is now. So when that light gets emitted, the atoms are so close together that that light bounces into atoms. And that means it's not traveling far enough to get to anybody, right? You emit it, it immediately gets absorbed. It's like you're going to a concert and you're all jammed into the concert. You're trying to get something to somebody, but every time you move, you bounce into somebody. You just don't get anywhere. Slowly but surely, the universe expands. Your concert venue gets bigger. People get farther apart, and now you can move. So we need two things. We need the atoms to make light, and then the universe has to expand enough that that light can travel. And once it travels, then we're at the 300,000 year point, right? At 300,000 years, the universe is cooled enough and gotten big enough that light can travel. That light's been traveling ever since then. We pick up some of it now. And that's that background radiation. So we need those conditions to happen.
Okay, so you have light sources. I don't know how far the furthest source we can see out is now, but doesn't light disperse over distance?
Yeah, it does.
Okay, so if it's that far away, how can we see it at all? Isn't it so diluted by the time it gets here? You can't see it?
Yeah, it's very dilute, and that's why we need really, really big instruments to collect enough of it and to stare long enough to be able to find it, right? That's exactly what you're looking at. It's a very diffuse, very dim thing, and it takes special instruments to be able to find it.
All right. It seems
for exactly that reason. You're right.
If it was so dispersed, then all of the billions of sources would also be dispersing. So it would be just one soup of undiscernible. You couldn't see any source because all the light dispersion would be all mixed up by the time it got here. Seems like.
Yes, with one tweak. So you're exactly right. And the one tweak is in this very dense universe, as it's expanding, not every point is exactly the same. Some places are a little warmer and some places are a little cooler. Some places are a little denser. Some places are not quite as dense. So as it expands, you don't get a uniform soup. You get a slightly different soup from place to place. So if you look at there are several famous pictures. One's from the Planck satellite, one's from the WMAP satellite, and what's something called COBE. There's a map of that light because you can measure it at each spot. And the differences from one spot to another are a few hundredths of a percent difference. Very, very small, but you can map it. And yes, it looks from the first way you look at it, it looks like it's pretty much the same everywhere. But then when you look closely, there are slight differences from place to place. And that tells you what that density of the universe was at the point that light, that all of that light could travel.
Will the increased ability, computational power help define those sources of light?
Oh, yeah, absolutely. The fact that simulations can now be run at, in reasonable lengths of time on computers is definitely a very big part of this.
Okay, sometimes, well, a lot of us hear about quantum computing. It's really pretty fuzzy for most people, including me, mm-hmm. and it shouldn't be so fuzzy for me. But I do want to get to that. The journey to get from where we are to that is going to be illustrative. So, back to how light is made by electrons moving around from place to place, distance to distance in little segments or quanta, produces energy. And those are particles. And you'd expect, and I'm trying to whip through this as fast as I can, because to get caught up in this would be a separate quagmire, as you know. So way back, I don't know, turn of the century, before the turn of the century, somebody noticed that, hey, some lights have different colors than others. And they experimented with trying to figure out why that was. And that led them, the experimentation with that led them step by step to the behavior of light and that little gold leaf trick when it was the electricity, you shine a light on it, the photoelectric effect,
Photoelectric.
right?
Right.
Shining a light on it would knock the electrons off or something, and these little experiments led to wondering about the behavior of light and how it behaves like a particle. It's a wave, light waves like sound, but it behaves like a particle too, which brought folks to an experiment called the double slit experiment, where they would shoot a bunch of electrons through a slit, and it would form a pattern at the back on a screen, which behaved as if there were water going through there, and the waves. It exhibited wave behavior because it acted just like a wave, and if it were water, you go through the slits, and it would make two separate wave formations, which would interfere with each other in some places and double in other places, creating a strip of light on the back screen.
Right.
But the weird ass thing that happened is at some point they started shooting one photon at a time, or one electron, whatever they were shooting, one through a slit at a time, and you would expect that what you would get is just a pile of little dots on the back screen because the thing shot through and hit the back. But no, it still, even though you did that, behaved like there was something going through both slits. So, and here's, of course, I have my big beef. Here's where they said, oh, well, you shoot it through there and it's going, the reason it's behaving like a wave in the back is because it's going through both slits. You shoot one through a slit and somehow it goes through both slits. Correct?
Well, actually, if you can shoot one electron at a time, which you can't easily do, but you can do it, you actually show that the electron goes through one or the other.
Okay.
And when you have a stream of those electrons going through, you get the patterns, the diffraction pattern that you described, that pattern of brights and darks.
So,
and so that becomes the confusion that really, in a way, makes the situation worse, because it says when you shoot an electron is a particle, and you go, well, a particle goes one place or another, and it behaves that way. But when you put a bunch of them together, you say, but I get this pattern, and therefore they're behaving like waves, and they're interfering with each other.
All right. Well, I have a theory on that.
So I mean, it takes heavy drinking to be able to sit there and think about these things.
I have, polish up my Nobel Prize, because here we go.
Yes.
When you shoot, I don't think it's an empty space. I think it's in a field, some sort of field. And when you have an electron going through, it causes the field to act like a wave. And somehow guides and then causes the electron to behave as a wave.
Right.
It's not an empty space. But instead of coming up with something sensible like that, this whole group of people called the Copenhagen group, headed by Niels Bohr, said, oh, no, not that. It's everywhere at once.
Right.
And since it worked, since they didn't bother to figure out why, no one cared for 50, 75 years why. No one looked into it. And anyone who did look into it wouldn't be able to get a job at the university. It was an anathema to even look into it. Don't just shut up and compute, as they say.
Right.
But I think that's lazy, and they're expecting me to believe something can be everywhere at once and throw out logic, which has also worked for a long time, that says something cannot be both X and not X.
Right.
Which has worked pretty well for a long time. And there are other things that make me doubt it. So if one can be everywhere at once, is everywhere at once, then what if you have a bunch of them? They can't all be everywhere at once. Because if you had a billion of them, they can't all be everywhere at once. That tells me there's a problem with that. They're moving around, but if they were everywhere at once, bam, they'd be competing for space and, I don't know, blow up, or just what would happen?
Yeah, it's very strange. The whole picture is strange. There was that theory that said that the Schrodinger waves are just guide waves, right? You're calculating the guide field, something very similar to what you just described.
Yeah.
And the particle follows that field and does what it does. And what you're really calculating is a field distribution, which gives you a probability of which, like you're in the game where you pull a thing back and the ball goes through stuff.
Right.
Yeah, sort of like, well, it'll determine which
Plinko.
path it takes when it comes in.
That's Plinko.
So there were those who worked on that for a long time, and it's very strange, all these different pictures of quantum mechanics, and it's very clear. Anybody who says they understand quantum mechanics is lying.
Okay. So what that group of people is saying, that until you observe it, you have to assume it's everywhere at once, which I don't buy. Until
Right.
you observe it, it's everywhere at once. That's called superposition, right?
It says that it's not that it's everywhere all at once. There's a probability distribution of whatever, and it's an overlay of all the possible things it could do, right?
Okay,
That's
so when they
superposition.
say it's
all the
everywhere,
possible things it could do are all happening at the same time until you look, and then it says, no, this is the one I was doing. I'm going to just do that one thing, and yeah,
Okay.
that's the probabilistic
so
idea.
since you cannot make a judgment on, say, where a particle is until you observe it, their theory says you have to assume it's everywhere. And it doesn't become what it is, either spinning right or spinning left or whatever other either or properties it might have, until you observe it. But I believe that capturing of the thing is not from observation per se, it's from hitting it with light.
Right.
But you can observe things there are ways to observe things without using light as an observer, right?
No, not
you
really.
can
No, because remember, everything is fundamentally light. In other words, every interaction that you have ultimately involves what we call light. It's not necessarily the visible stuff you see. So the atoms in your body are held together because the electrons and the protons like each other, right? That holds the electron in place. But what they're really doing is they're exchanging light. That electric force that holds them together is really represented by a kind of light. The math is the same as the light you and I see, but it's much, much tinier, much higher energy. So every time you interact with something, so even the fact,
so go ahead.
no, so even the fact that you're sitting on your chair and you think you're sitting on a chair, you're actually not. No atom of yours is actually touching the atom on the chair. There's electricity pushing those things apart, and that's done with light particles. So every interaction, just you say, well, I can measure it because I can touch it, and you're touching, you say, what I'm touching, well, actually you're not. The atoms in your finger and the atoms what you're touching are exchanging light. And that's where light becomes fundamental. So there's always energy involved in every observation. Some form of energy exchange happens every time you interact with anything.
So we're getting to the quantum computing part, folks, because that's
Right.
based on the thing called superposition.
Right.
And we're trying to understand what that is. So there's no way to measure even the path or whether an electron or particle has been through here without light.
Without doing something to it, you can't tell where it is and what it did. That's right. And so until you do that, these particles, these waves are interacting and doing their thing. And then at the point that you interact with it means it's a particle of light and it hits a detector, like your camera is doing right now, or it's a set of electrons and you let them hit something and you detect them, any kind of interaction like that, it then condenses down to one of these possible states.
All right.
And
So go ahead.
no.
Do electrons go in a straight line sometimes and not a straight line other times?
Well, it depends what you're interacting with. Remember that there's always stuff everywhere in the universe, and nothing goes in a perfectly straight
Yeah.
line.
Okay.
But the point is that in a quantum computer, where this is all being done on very small scales, right? In tiny little cells, we have different things that are happening. In optical things, you have optical light going back and forth, and these photons aren't talking to each other. They're interacting. We don't know what their state is until they come through, and we have something called a polarizer, and it says, oh, this is how much of it was pointing in this direction. We don't know that. In between, it's pointing, to take your case, one way to look at it. Those things are pointing in all different directions all the time, but one of those directions is going to come out when we finally look at it. And
Okay.
that's your answer from a computational standpoint. That's a zero.
So now we get to quantum computing. How does a quantum computer work? It works because it's not an either or situation. It's a matter of probability. So somehow that exponentially gives you more computing power.
Right.
That's a big gap, but I don't know. How does the quantum computer work?
So a quantum computer works because you create, bits, just like you have bits in a computer, but a computer bit is strictly a 0 or 1. Either there's electricity in that little magnet or there isn't electricity. It either goes one way or the other way. It's a 0 or a 1. That's what you got. But if you put a number of atoms together or a number of particles of light together in an area and you keep them together, that's why quantum computers have to be very cold so things don't leak out. They interact with each other, and whatever the quantum is for each of those things, they get into what you call a superposition. There are all these different combinations of ways that those things could be together. We don't know what those are until we have, quote, a measurement. That measurement might be we send a pulse of light through it. That measurement might be how much magnetism is in there. That might be whether a particle can leak out or not. Different ways that we can then say, okay, what is the state of this combination of things together? And that state tells you your answer, if you wish. Just as your computer tells you an answer by it kicks out a collection of zeros and ones. This is kicking this out as well.
And what does it kick out again? What is the quantum computer kicking out?
It kicks out, you measure, you can detect what the state is. You have this collection of states, collection of different combinations of things that are together, and a particular one of those states is the one that you detect. So as you said before, something can be spin up or spin down, right? We can put a bunch of particles together and they're pointing in different directions, right? They're spinning in different directions, but those spins are talking to each other, okay? That's this quantum thing, because they're in the same area, they're lining up in different ways, and each one can be up or down with some probability. Just probability, we don't know which way it's pointing. You put a magnet on this thing, and they're going to line up with the magnet, and when they do that, they're going to either need energy in order to move in the right direction or give up energy to flip in the other direction. So you can measure that energy, and that tells you what was the combination that was actually in there. That combination is going to tell is a zero. Basically, it gives you the answer when it comes out, right? Just the same way in your computer, zeros and ones, your processor is putting out zeros and ones. This thing is putting out its equivalent of zeros and ones, but it's doing it by overlapping all these things together. Now, realize this one pile we put together is one bit. You need a bunch of them, just like your computer can't do anything with one memory location. You need a bunch. You need a bunch of these, and each of those taken together is a piece of your puzzle. And then when you get it out, you get the number, which is the result of your puzzle. And because it works with probabilities, it can look at very complicated problems and narrow down what the outcome is. Whereas with a digital computer, you have to calculate every one of those possible things separately and then add them up. This can do them all at the same time because those atoms, these electrons or atoms or photons interact with each other very quickly.
You should write a book on quantum computing for not dummies, but explaining. I mean, somebody done it already? You should do it, because I want to know. Even with your excellent explanation, it's a little fuzzy. It seems to me. Here's one. So with a regular computer, you type in something, and it is programmed to convey what you typed in with a series of preset or programmed zeros and ones, right?
Right. Mm-hmm.
Okay. But with a quantum computer, it's not the same every time. Like with the zeros and ones, you type in XYZ, and it's been programmed so XYZ spits out the series of zeros and ones, and something pops on the screen. you know every time the same basic thing is going to happen. I don't see how you corral the probability to be repeatable to make things happen. The same thing happen when you type in XYZ each time.
So
It's
let's go
different.
back and just briefly talk about where computers started. So if you think of the most fundamental computer, you have a bunch of switches and a battery over here, and depending on how you set the switches, you add these things up, you get something out, right? And if you turn these on and you turn these off, you get this thing. And that's completely deterministic, right? You know exactly if I
Right.
throw these switches, what thing I'm going to get.
Right.
It's just there's so many combinations, but you throw the switches and you do it. And you'd say, okay, but that only solves one problem, right? I have this thing and it can add up 8 numbers because I have 8 sets of switches. I put them on, I get the answer. The thing that Alan Turing did, and he really developed this during World War II, was to build a collection of switches which could be programmed so that depending on how you hook them up, which is what we now call software, right? It will then solve the problem that you've asked it to solve. Otherwise, it can only solve one problem. Add these 8 numbers. That's all it knows how to do. But if you have this set of switches, which is all a computer is, right? The computers we're talking on now just have tens of billions of these switches.
Mm-hmm.
And we now have a thing called software, which is just telling how are you going to hook up the switches to
Right.
do this particular thing or not. Now,
Okay,
that's a
completely
big part
get
of
that.
quantum computing is figuring out how to build the stuff to make the collection of qubits, these little ensembles, do a different problem each time. And you're exactly right. That's R&D that's being done right now by big, powerful companies like Google. How do we build this so it'll do that?
So there is no such thing as a quantum computer yet.
There is no general purpose quantum computer. There are special purpose mini quantum computers that have been made that can solve individual little problems and show that those problems, which would be almost impossible to do on a conventional computer, are doable on a quantum computer. That's where they are. It's not
So at
something
some
you can go down to your local electronics store and go buy one, put it on your desk and say, please figure out what I should serve for dinner on Tuesday. It's not there yet. Give it time, it will be.
Gradually, my understanding will fill in. Now, what are some of the applications for quantum computing that we can barely imagine now, that only the people who think about that have thought up, that we just can't do now? What will we be able to do in the future?
So think about weather forecasting.
Yeah.
Weather forecasting means we take information that's temperature and humidity and wind and ocean currents, and you throw all of this into a model to try to figure out, is there going to be a hurricane hitting Florida on a given day and what it is. And if you watch your weather forecast, you'll say, here's the cone. We know the hurricane's going to be somewhere in that cone over the next few days. We don't know exactly where it is. That's because the problem is way too complicated to solve. There are just too many things. Different altitudes, different latitudes, different longitudes, different temperatures. Well, a quantum computer is going to be good at doing that because it can put many pieces of information together and work out the probabilities of what's going to happen, because you can mathematically show that you can't exactly solve it. You can only get a probability distribution, and a quantum computer is going to be really good at doing that. So that's the kind of problem where you're going to expect much better weather forecasts in the future, because this thing can put that stuff together much faster than any reasonable computer now. And so that gives you an example of something you could use.
How about medical application?
Much the same kind of thing. If you're trying to understand drug interactions, brain functions, neuron things, those all behave under similar mathematics, and quantum computers will hopefully let us figure some of those things out and be able to work things out.
Okay. I suppose just like weather, cancer is a series of probabilities. There's a number of factors.
Mm-hmm.
Genetics, irritation, chemical irritation, other kinds of irritation, a bunch of factors. It's just a matter of probability, and maybe a quantum computer can, figure out the probability that you'll get it, maybe so that you can do a prophylactic treatment, or maybe the probability of what kind it is without a biopsy, stuff like that, or
No.
and the probability that some set of chemicals in a medicine will work on this particular type of cancer.
Yeah, the bigger place where it'll contribute to things like cancer research is doing things like modeling proteins and enzymes, understanding at the molecular level what's actually happening. Why does a cell stop dying, right? Cancer is just cells that refuse to die. You just keep accumulating them and you end up with tumors. And then it can send things out and tell other cells not to die, and you build up too many cells, and those are tumors. Well, why do those proteins do that? Proteins are very complicated, right? There are hundreds to thousands of atoms in a protein. How do you model what the shape is, what it's doing, what configuration could it have, how would it interact with all the other proteins that are around in your body? That's the kind of problem a quantum computer is going to be really good at solving. Now, when you figure that out, and you say, oh, this is what happens to the proteins, then you can do the chemistry and say, well, how can we keep that from happening, right? What do we have to do to keep that from happening? It's like you look at bricks in a house. This is a bad analogy. You say, okay, this is what slowly happens. That the mortar starts to corrode, and then the brick doesn't hold up, and then this happens. You say, oh, wait a minute. If I understand that, I know how to keep the mortar together. Well, maybe we can do that chemically and say, this is a way we can stop those proteins from accumulating the way they do, and that's going to keep this from happening. Or we can develop this enzyme. So as proteins do this, we can give you this enzyme that'll break those proteins so that they're not going to keep building up, right? You can either keep it from happening or you can break it after it starts happening. The same thing with Alzheimer's, right? Alzheimer's is a protein buildup in the brain. We don't know why that happens. Can you figure out a way to break those proteins up or to keep them from building up? That would be great, wouldn't it? If you and I could have the same intelligent conversation when we're 90, wouldn't that be great?
Yeah. Okay. So we've covered a lot of ground, but we're not done. I don't think we've really covered, of the three things, what we know, what we don't know. We've done a lot of what we don't know, but have we really covered what we can never know? What we can't know?
I guess as a scientist, and this is where you really get into philosophy, is are there things that can never be known? And when you talk about the quantum mechanics stuff, is it possible that there are things that cannot be known? You can determine what the state of something was after you measure it, but what was the state before you measure it? Maybe that is a thing that can never be known. I don't know. I mean, I really don't know. But that gets into some of these really questions that are philosophical, not questions that are physics anymore, right? About what is unknowable. As a physicist, we try to think that everything is ultimately knowable. We just don't know how yet. But maybe there are things that are truly unknowable. That's interesting, don't you think?
Absolutely. I guess I don't like to think anything is unknowable. Why would it be unknowable? We can't see a lot of stuff, but we can see the results of it. Like time, I think maybe time doesn't act the same in all circumstances.
We know it doesn't.
Well,
we know that time and space
in
and mass
addition to the
connected.
speed factor,
Right.
in other ways, in other places, maybe. I don't know, but
Yeah, I mean,
I was wondering if the particle level, time is different somehow.
Yep.
And stands still, so the particle can completely go everywhere, and no time has passed. And that's like superposition, and time stops for the thing.
Mm-hmm.
It moves without time, so it has endless amount of time to be everywhere.
Right.
And then when you observe it, time begins again for it. I don't know, something like
Cool
that.
idea. That's
All
a
right.
really cool idea. That's an interesting concept. Yeah, absolutely. Those are really interesting things to think about. Wonderful.
We
thing.
have a very interesting viewer named Dizzy. I don't post all comments, but this is a good way to finish up here. Speaking, we talked about light and distance. He says, quick math. The last BCN broadcast, which was in 2009, in August.
Mhm.
He says the last BCN broadcast is now 6.842 E
10 to the 15.
15 miles out in space. But that's okay. That's if it was transmitted by the radio signal, and that goes at the speed of light. If there was somebody on the other end with a big giant receiver, could they hear it? If they, had the same technology we do, or does it get too dispersed?
Obviously, the farther things are, the weaker it gets. But in principle, just as we can build instruments to detect very weak things, you just need a bigger and bigger instrument that somebody elsewhere could do that. By the way, that number is too big, because 1 light year is 6 trillion miles, 6 times 10 to the 12th. And so you're going to have a number that's on the order of 10 to the 13 miles, not 10 to the 15. It's not quite right. But in any case, it's a very big number. It's a very big number. But if you have a broadcast that you said was from the 90s, so it's 30 years ago in rough numbers, 30 years means the stuff can move at most 30 light years, which means it's just reaching the star Vega now. Vega is 28 light years away. So that signal is reaching relatively nearby stars, a few dozens to hundreds of stars. So if there are things going around those stars that are pointing in this direction, they go, hey, yeah, we heard a WBCN thing. I wonder what the heck that is.
But, yeah, but there's so much so many radio shows going on all the time. Wouldn't it be just one big, confused mess?
Yeah.
Okay.
Yeah.
And one thing to think about that I think is fun is if you want to send a message into space, if you have a laser pointer and keep it on for 1 second, it sends a message 186,000 miles long into space. That's so cool.
Isn't that amazing?
Boom. Yeah. You just sent a thing 186,000 miles long, a chunk of light shooting into space.
Yep. And it will keep traveling until it hits something.
Dizzy says, I was doing quick math.
Yeah.
He changed it.
Yeah, 8 times 10 to the 13. So there, I told you it was going to be about 10 to the 13.
So I'm afraid, Dizzy, we're going to have to, give you a cross on that. You got that problem wrong. But next time you'll get it right. Dizzy is one of the coolest guys, and he participates a lot, and he's been with us for a long time. Cool. Well, this has been a brain buster. I appreciate it. If you come up with a book, by the way, the hardest book I ever read, the most difficult book, was one that Doug sent about, how would you describe that book? It was about the idea of...
A book by Lisa Randall, who's a great physicist, and you talk about the universe, and you're looking at multi-dimensional universes and how multi-dimensional universes could work, where they might come from, and how we could investigate them. It is very mind-bending because we don't envision things in more than 3 dimensions. So
and what she tried to do and did a pretty good job of was in using the English language, which is a great language, but it's in a limited tool when you're talking about multi-dimensions. She was able to kind of draw diagrams and use language to give you a little kind of inkling of what it might be like. As best you can. It was a little something. And it's interesting because, there are big chunks of stuff I really don't understand. But when you read one of those books, you just got to do the best you can and keep going. And you pick up what you can. So if you come up with a book that really helped me really get a firm grasp on the back to the simple double slit experiment and the extrapolations of it and the various ways they tried it, I'd appreciate it because, did they try it with 3 slits? Where they find out? Did they try it with 1 slit? Did they try it with no slits? Did they move the field back closer or further away? And I'd really like to have a book that told all that stuff. And if there's
one for you.
And if there's this quantum computing book that maybe visuals would help, maybe if the author can do what the author of the Dimension book did, kind of give me a thing in my mind. Oh, by the way, so you have particles colliding in a computer. I mean, in a collider. Do they go in a straight line, and they hope they can't
No.
hope they just do they just throw a bunch of them and hope some of them hit?
So part of accelerator design, one of my grad school classmates worked in this field quite a bit. You have a set of magnets so that particles will continue to go around in what is basically a circle. And you set particles going in one direction and in the other direction. So much like if you took an LA freeway and just mixed the lanes up, so everybody going northbound, southbound are on in the same highway. And you continue to accelerate them so that they are going as fast or have as much energy as you wish. And then those beams are steered at each other.
Oh.
So at that point, you have the collisions. Those collisions have a tremendous amount of energy, and that produces this sheaf of particles and radiation that tells you how those particles behave when they interact.
It must be so hard to aim them because they're so.
Mm-hmm.
And then are they sending a stream or individual ones?
It's a stream. It's a stream of current.
So when they get it lined up perfectly, then they must go bang, 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 because they're all in a row. They must.
Right.
And how do they know? When they're hitting each other. How do they?
Well,
detect
you have a large detector around it. So the Atlas detector, which was used to find the Higgs boson, for example, which surrounded the area where these things hit, is the size of a small building, and it has a tremendous number of detectors of different kinds, so that when these things happen and stuff sprays out, everything that sprays out gets collected. So one way to envision this, let's go back to our highway example, cars going in opposite directions. They're trying to avoid each other, but eventually two of them hit each other. Well, imagine you're trying to figure out what kinds of vehicles hit each other. But you can't go right to the scene. You don't have a movie of it, but you go and you look around, you go, oh, there's a fender over here, there's a wheel over there, there's a steering wheel over here, there's a hood over here. You can look at the pieces and you go, oh, that was a Ferrari and a Mack truck.
Okay.
Okay, and we know who lost that battle, right? But you could figure that out by looking at the debris, and that's how this is done. You look at the stuff that comes out. You have all sorts of ways of measuring that, right? You have things that collect those particles, and you can go back and go, oh, that's what made this.
So they're sending different kinds of particles, not exactly the same kind. So if you wouldn't have to figure that out if they were shooting the exact same kind.
Well, no, you're shooting the same things. You're shooting protons at each other or electrons at each other. Generally, you're shooting protons.
Okay.
At each other. Right.
Fantastic. Look, we've been doing this for almost an hour. Just like a class. I bet you there are a few folks out there. There are a few classes that you ever took in college in which you learned so much so quickly. That's what I'm thinking. I hope so. It's always, before you go in the last few minutes, talk about the things that you are involved with, Mountains of Stars and the Darkness Sanctuary program.
Yeah, so I'm very connected with the environment. We as people need to be taking care of the earth and the environment. Another thing we've talked about on prior shows with Bradley is, we're not going to move all the people off of this planet somewhere else. That's just not happening. Space is way too big. So we need to take care of the planet. And I think that understanding where we fit into the universe is a great way to get people to do that. So Mountains of Stars, the program that I run, aims to do that, get people out under the sky, looking up, seeing things, and understanding what that means. A lot of the things we've talked about today, when you start thinking about them, you start realizing how tiny this little rock is and what we need to do to take care of it. So Mountains of Stars is a big part of that, and getting rid of light pollution so that we can actually see that sky is an important thing. If you never see it, if you are in a city and you never see anything beyond the buildings, well, of course, you're not going to have a context for where you fit. So we've done a lot of work, including creating a dark sky park up in Maine and working with communities to try to control lighting. That's another big part of the work that we're doing. So we can connect all of you with, the biggest of big pictures, the universe out there. I think it's an important thing to do.
Is it an organization you can donate to?
Yes, there's a group called Dark Sky International. That will be one of the best places that they can engage with this big issue of light pollution. It's one of the best ways we can connect people with the universe is to do lighting right. Not to get rid of lighting, but to do lighting better. It makes life safer and healthier, and the stars come back. So look at Dark Sky International. Darksky.org would be a good place for people to go get involved. So let's have you do that.
Perfect. Doug Arion, astronomer, physicist, and my pal. I really appreciate you taking the time to answer all my ham-fisted questions. I appreciate it.
I have a great time talking to you, Bradley. We'll do this again soon.
Okay. Bye, everybody.